Welcome back to the Home Lab, and I've got an interesting video for you today. What we're going to look at is a little bit of atmospheric optics and why on a sunny day when you look up into the sky it looks blue, and then in the evening as the sun sets it goes a sort of reddy orange colour. So for today's video, I thought I'd go back to my roots and the FJ's physics videos I used to do in my laboratory at school. So what I'm going to do today is a short demonstration of why the sky's blue during the day and it goes a sort of reddy orange colour at night. And then after that, a quick explanation of the physics that's going on. And it's a little bit more complicated than you might first imagine. It wasn't until the late 1800s that this was explained by Lord Raleigh in the UK. It was known since the time of Newton, of course, that light was made up of colours because he'd done his experiment with prisms and showed that white light from the sun was actually made up of the colours of the rainbow. But no one was quite sure at the time, and there were many arguments about whether light was a wave travelling through space or a series of coloured particles. Well, Lord Raleigh's explanation uses the wave nature of light, so that's what we're going to use today to explain what's going on. But it's quite interesting that the corpuscular model, the model of light as little packets, came back a bit later, in fact, to show and explain some of the quantum properties of light. Taking light as a wave, we know that red light has a long wavelength and green light a shorter wavelength and blue light an even shorter wavelength. And Lord Rayleigh showed that the scattering was inversely proportional to the fourth power of wavelength. So what that means is as the wavelength gets smaller and smaller and smaller, in other words closer to blue, the scattering of the light goes up much, much more. Now what I mean by scattering is the light travelling through the air past the air molecules, or I should more correctly say the nitrogen and oxygen in the air, gets thrown out in all directions, and preferentially it's the blue because the blue is closest to the size of those molecules. Its wavelength is still much smaller, but the red tends to penetrate directly much more effectively. So it's these ideas of scattering that we're going to use to explain why the sky appears to change colour from the blue of the day to the reddy orange of the evening sun. So to demonstrate this, I'm going to take a clear tank of water that I've got here and I'm going to shine some light through it. Now the clear water you imagine as being no particles, as being deep space. So if we shine the light through it, the side of the tank doesn't really get bright at all, but the end is very, very bright, which means that all of the colours pass through quite happily without being scattered. But what we'll do now is add a few particles to the tank and see what happens in terms of the scattering. So I'm going to add some particles to the tank now, and the way we normally do this is with a few drops of milk. So let's pour a little bit of milk in. There we go. And you'll notice, interestingly here, it's really, really white. And that's for a reason I'm going to explain later. It's not just milk appears white. So let's give it a little bit of a stir and get those particles to spread out all the way through the tank. And what we'll do is we'll take a closer look at what actually happens to the light and how the colours change. But the first thing you'll notice is that the light at the end has changed colour, it's not as bright. And can you see the sides of the tank are now appearing a sort of milky blue colour as the light goes through and the blues are scattered off the milk particles, but the reds, yellows and oranges travel through quite happily. So just for fun, we'll add a little bit more milk. That might be too much, but we'll see what happens anyway. Stir it in. And now we're getting to the stage where it's a very low sun. It's a sort of evening sun. And again, if you look over here, you can see it's getting really orangey. So here's all the blue light being scattered towards me and towards you and the camera. But if we were to view from this end, looking that way, we would notice that the torch itself appears really orangey. In other words, the evening sun, when you look at it through a big thick layer of atmosphere, has had all the blue light scattered away, and you only see the orange and reds. So to explain this, if you remember that white light is made up of a whole series of wavelengths, and we consider the red light to have quite a long wavelength as it travels through space, the green light a shorter one, and the blue light an even shorter wavelength. And the crucial bit here is that the air around us also contains lots of little particles. So if I imagine the air being here with all its particles in it, which is nitrogen, oxygen, and later on we'll talk about a little bit of pollution. These particles are still very large, but they're closest in size to the wavelength of the blue light. Remembering the wavelength can be considered to be a measurement from the top of one peak to the next peak. Call that lambda. So the white light's coming in. Obviously you can't do that with a white pen, so I'll just put W on there. And the blue light, as it comes through, hits some of these particles and sort of scatters off it in all sorts of directions. And so you can imagine the light not reaching our eye directly very well. Some of it will get through, and some of it will scatter such that it might come towards us with us viewing from here. But most of the blue light has been sent off in all sorts of directions, and some of those directions you see are around us. So when we look at the sky at different angles and not directly in the direction of the sun, I'm not saying look directly at the sun, but you know what I mean. But if we look away from it, some of this scattered blue light reaches our eye, and there's very little scattering of the other colours, so that bit of the sky appears blue. But the red doesn't scatter very well, so that generally travels straight through. So if we're looking at a very thick layer of air, we're going to get a lot of scattering of the blue light, and so the sky around us is going to look blue, and directly in front of us it's going to look a little bit more red. Now, the crucial thing is that at night we're actually looking through a thicker bit of atmosphere. So if this is the Earth, and here's the layer of the atmosphere, we can call that the Kármán line if you want, which is about 100 kilometres up. So I'll just shade in the Earth. Very quick diagram, of course. If we're standing here on the Earth's surface, during the day, if we're looking up, we're seeing the sun above us, and so we're seeing the light coming through very brightly, but looking sideways, we're seeing all this scattered light. However, at night, when the sun is down here, sort of kid's sun, now what's happening, of course, is the light that's travelling through to us has had a huge distance for the blue light to scatter off in all directions, and basically nearly all of the blue is lost, and it's only the unscattered red that makes it through to our eyes. So during the day we've got quite bright light from the sun, and we will be seeing most of the colours, but a lot of the blue is scattered. So when we look away from the sun's direction, remember, don't look directly at the sun, the sky appears blue as all this blue light has been scattered around and some of it enters our eye. Whereas at night that scattering is such that almost none of the blue light gets to us because it's gone through a much thicker bit of atmosphere and has more chance for scattering away, so that all that's left to reach our eye is the unscattered red light. So the sun setting will look very deep and red. Oh, by the way, it's worth saying, what would happen if the Earth didn't have an atmosphere? Well, if you think about it, if we looked up, we'd see the light from the sun. But if we looked in this direction when the sun was overhead, we wouldn't see the sun at all. There'd be nothing for the light to scatter off, and there wouldn't be a direct line of sight. So space would appear completely black. And I'm sure you've seen those images above the Earth from NASA, where they look towards the Earth and you see the oceans. Obviously you see a bluish effect there, but you see this blue haze around the Earth, which is its atmosphere, caused by all the scattering of the blue light back up towards the astronauts. But if they look away in any direction other than at bright stars, galaxies, and the sun and moon, the sky will appear completely black because there's no direct light getting to you and there's no scattering that can happen if the sun is at a different angle because there are no particles for it to scatter off. So here's the experiment repeated with a much brighter light source, a much hotter one, not as hot as the sun, but you get the idea. So we've got a halogen lamp over here, and you can certainly see as you travel along the tank, the colour changes. We do get a little bit of scattering here of the red, but if you look at the end, the light that's coming out is really a deep orange, sort of reddy colour. So most of the blue light has been scattered away in all other directions with only a tiny amount getting through. So here we've got mainly wavelengths in the red end of the spectrum. Oh, the really curious amongst you might be asking, well, hang on, why does the red appear to only scatter at this end of the tank? And that's a really good question. But of course, it's scattering everywhere. But the red that's scattering here is scattering with the other colours, and especially the blue. So it still looks a sort of bluey tinge or fairly white. But by the time we've got to the end of the tank, there's hardly any blue left to scatter. So the only scattering you're going to see is the reddy orange colour. Like my experiment, if you look closely, the sky can take on a milky hue as well if there are other particles of larger sizes, often greater than that of the light's wavelength. And if they're present, they also cause scattering, and they're things such like water, dust and pollution. With all the colours being scattered, the sky therefore will appear this milky white colour because white light's made up of all of the colours. And this type of scattering is a development of Lord Raleigh's work, and it's called Meyer scattering after a German scientist, and it explains why clouds can appear white, but that's perhaps the topic for another video. But just before we finish, a little bit of a story. Many years ago, I took an expedition to Easter Island, and that's a whole story in its own right. But I stopped off on the way at Santiago de Chile and then moved up high into the mountains and looked down upon Santiago city. And it was a bright orangey sort of colour. It was quite startling, in fact. And Santiago had an awful lot of public transport, which was buses, diesel buses, and they were all very dirty. And I may be wrong, but I'm pretty much convinced that the air around the city was so full of diesel particulates that any light that came down from the sun and then reflected back off the ground to me, looking down from the hills, had all the blue scattered out of it, and all I could see was the remaining red and orange due to the pollution in the air. So I do hope you enjoyed that video, and even if you thought you knew all about this subject, maybe you learnt just a little bit more about why the sky has different colours at different times of the day. Anyway, thanks ever so much for joining me, and as you know, I'll be making another video very soon.